So before we get started on the new material today, let me just recap for a minute what you learned on Monday. Okay, so hopefully you got a handle on the basic graphs of sine and cosine and how those come from plotting the points along the unit circle. And then also on Monday, you learned how to handle vertical shifts of the sine and cosine function. And I want to compare what you learned on Monday to what we learned when we were transforming functions like y equals x squared. All right, so remember earlier in the semester, or we also transformed functions like, this was an important one to us earlier in the semester, like radical x. All right, so you're supposed to know what these functions look like without having to graph. And I just want to compare, right, what you were doing if you were graphing something of this form with sine. So say you were doing something like y equals 2 sine x plus 3. Okay, and so what that did is it stretched the sine curve, right? And this is known as the amplitude, the 2. So it stretched it up on the y-axis up to 2 and down to -2. That's before I account for the 3, of course. All right, so first I stretch it up to 2 down to -2. Then this 3 takes that entire graph that I just stretched and it moves it vertically up 3 units. All right, so same idea when we were working with these functions. All right, so remember what this would do. If I have my standard graph of y equals x squared and I multiply it by 2, what that does is it takes my x coordinate 1, right? But now I have the point, instead of the point 1, 1, I have the point 1, 2. Okay, so it takes my graph and it makes it, it stretches it out. All right, it makes me get bigger faster. Okay, so that's what this function would look like compared to this function. And if I did something like that here, if I multiplied this by 2, right, same idea. It would just be up here. It would get bigger faster. Okay, all the functional values, all the y values are twice as large as they were before. Now, if I add 2 here, or if I had a function like y equals radical x plus 2, right? What that does is it takes the entire function, I'm going to change to blue for that one, it would take the entire function and just move it up 2 units, okay? Or this takes the entire function, right, moves it up 2 units. Okay, so I hope you can see the parallels between what we already learned earlier in the semester and what we're doing when we're working with transformations of these trig functions. So anyway, let's go over here and start talking about something new. First of all, on Monday, they talked so much about the range of sine and cosine. What about the domain? I feel like that kind of got lost in the shuffle. So remember, domain is input. What can I input, or what are the possible x values for sine and cosine? Remember, I input an angle, right? Well, what can an angle be? We know an angle can be negative, right? And that's why this keeps going and going in this direction. Angles can be negative if I go backwards around the circle, right? You know, this way I've got a negative angle. I also should recognize, because the values of sine and cosine come from plotting the points along the circle, you know, is there such thing as an angle of, say, 10,000? Right? Would that make sense? An angle of 10,000? And it sounds weird, but an angle of 10,000 would just mean I've gone around and around and around and around the circle, right? But an angle of 10,000 would have some reference angle that would be between 0 and 360 that I would be able to plot, right? To plot the x coordinate for cosine or the y coordinate for sine. So this, I showed you out to about 40, but this would keep going and going and going because I can go around the circle forever and ever and ever. And that's what makes the domain of sine and cosine all reals. I can input negative angles, I can input any angle because I could divide it by 360, right? Find out how many 360s went in, and then I just look at the remainder actually after I divide by 360. So that's the range and domain. And then we're going to talk a lot today about complete cycles of sine and cosine. So how do we know when we have completed a complete cycle? And for the cosine curve, one complete cycle of cosine, which happens between 0 and 2 pi. So 2 pi is 2 times 3.14, so about 6.28, which I can see right here, about 6.28. A complete cycle of cosine is when I go from 1 back to 1. Okay, so in this example, right, here's another cycle of cosine. So like if I box them off, this is one complete cycle of cosine. This was one complete cycle of cosine, right? Here's another complete cycle of cosine, right? Every time I go from 1 back to 1. Okay, for sine, a complete cycle of sine. Maybe I get a fresh piece of paper. A complete cycle of sine, right? The sine curve starts at 0, and in this time, now this should be perfectly symmetric. This should be the same length as this length, so my drawing's not perfect. But in the time it takes me to do the positive hump back to 0, then the negative hump back to 0, that is one complete cycle of sine. All right, and again, it takes 2 pi, an interval of 2 pi, to complete one full cycle. 2 pi is once around the circle, right? So if I go once around the circle, I have a complete cycle of sine. Okay, but then I could go around the circle again, right? And here I am at 4 pi, right? And I just got another complete cycle. So from here to here, I just drew another complete cycle of sine. All right, so what I'm going to look at next then is changing how many cycles I can get during a certain interval. Okay, so let's stop for a break.